the operation result true. And then I'm going to resume again with the operation result false. And I'm going to concatenate these two results together into a larger list. So if you have the 42 with all choices, you'll get back a singleton list with just the 42. And if you handle this program to toss the coin with all choices, then now you will get back a list with all the options when the operation result is true and false respectively. Yes?
The reason we don't use the X in the case of choose, or the reason we don't use the X in any of choose and fail is because these aren't parameterized?
It's because they are all units. So that's not useful. So if we look at the signature again, it's basically saying they all take. Yeah, but you can have operations that actually pass meaningful arguments. So what's more interesting about effect handlers? So far we have seen programs that just perform one operation. But there are also programs that could perform multiple operations, right? And what are you going to do with multiple operations? If you have multiple operations within a program, you have to handle them using multiple handlers. So in the case of jump toss, because you have both the operation choose and fail, now you have to apply two handlers in order to get the result. So in this case, we handle jump toss first using the handler for maybe fail that turns the program type into a maybe. And then we handle it using all choices that turn the type of the program into a list. And what you have now is a list of maybe. So because when you have multiple results for those choose and for these choices, like they can be true and they can be false. If it's true, then you can have you have this choice again, which can be true and which can be false. And in each case, it's going to first wrap inside the return clause of maybe fail that turns them into just. And then this whole result is going to be concatenated together in the handler of all choices. So you get a list of maybe. And another useful thing about effect handlers is that you can actually switch the order of handlers. You can switch the order of handlers and you will get different results. So in this case, I'm handling the same program with the same set of handlers, but I apply them in different order. So I will first handle the program using all choices, and then I handle it using maybe fail, and the result is nothing. Why the result is nothing? Well, this is because in this case, well, the choose will again have true and false respectively, right? And then this, but in the case choose is false, in the case choose returns false, you are going to call this fail immediately. And because this maybe fail is the outer handler, and this handler basically says, as long as fail happens in a program, this whole program is going to become nothing. Right? The order those handlers are applied, they matter. And you can also think about that from the types perspective, right? In this case, maybe fail, in the first case, maybe fail will turn into a maybe, all choices will turn to a list, so you get a list of maybe. And in the second case, all choices will first turn the program into a list, and then maybe fail turns it into a maybe, so it's a maybe of a list. And then as long as one exception happens in a program, you get nothing. Yes?
So if maybe fail is a maybe of a list, I'm wondering, you may be thinking of this wrong, but what does the list look like if we don't do maybe fail? Is it like heads, tails, and fail, or is that just not well formed?
So maybe it's like similar to what you would get in the first case. Or you are imagining that maybe fail would also return a list.
Or I think my mental model of this is all choices is going to be a list with each result of the computation. So
right.
It's going to give you a list item which is head, a list item which is tails. And I'm wondering, is there a list item corresponding to the fail?
just want the order, then you will just get nothing back. Yes?
I think maybe kind of the same question. What would happen if you have this fail there and didn't have like a handler around it?
What would happen if I have?
What would happen if you run the jump top program that only would handle all traces and not with baby fail?
Then your program would get stuck because there's nothing that handles the unhandled operation, which is fail. So the program has to have all the handlers available in order to run. Is that a question?
The handler composition seems kind of similar to mono transformers.
Right, that's a very good point. So I do have one slide for that very quickly. So you can consider, again, effect handlers as a more modular approach than monad transformers because you never write lift. Because if you have a stack of monad transformations, then in order to perform operations from the outer stack, you will have to lift it. And maybe you have to lift it many times depending on where the operation is in the monad transformer stack. And here you can see we just perform the operation without caring about the order of the handler. And you can actually apply the different orders without having any lift, and then you get the semantic stack. Okay, so with that, now we can actually expand our previous definition of the calculus. This is now this is the calculus we had before. So let's now try to expand it. Now that we have handlers. So the first thing we are going to do is we are going to add the syntax for handler. So in this case, I will write handle HE. So we are basically handling the computation E using the handler H. And H, in this case, is an operation clause written this way along with a return clause written this way. And in practice, you will see sometimes you will not write return clauses. That just means return clause is an adaptive function. Then there's nothing special about it, and you just omit it for simplicity. And we are going to add one more form of evaluation context here, which is you can evaluate something within a handler, and that tells you that this handler is currently available to handle operations. And we will add two more rules for the operational semantics for handlers. So there are two cases for the handlers. The first is if the computation you are handling is already a value, or becomes a value after some reduction. Then I'm going to take the return clause from this handler out, which is this f, and I'm going to apply f to b. Or if your computation being handled actually performed an operation that needs to be handled now, then I will try to find in this stack of evaluation context the innermost handler, again, that is extracted using this notation that basically says no handler in this capital E will handle this operation. So the H you find is the innermost handler for it. And now the control of the program for this part is going to be completely switched to this handler. And now the handler can decide what will happen. And handler decides that by applying its operation clause f that we take from the handler, and we apply it to the argument to the operation as well as the continuation. And the continuation is, again, it captures from where the operation is performed to where the handler is used in the evaluation stack. And as long as you give it back some operation result, it will resume the original computation and produce some result. And the other thing I should say is these 5 rules, they are all reduction rules that could happen under evaluation context. That's why we have this definition of the evaluation context, because you could imagine that this data reduction happened necessarily inside other applications. And also this operation is handling deep inside a program that is handled by some handlers, but outside of it, there can be more things happening. And then this is why we call this continuation delimited continuation, because you only capture up to the point of this handler, and you don't capture what happens after this handler. Right? Like you can have a program complete program that has lots of reductions happening, and they can all happen within the evaluation context. So with that, we can see more examples. So this basically is the standard effect handler calculus that you will see a lot in literatures. So if there's a paper about effect handler calculus, you will see like this being a subset of that calculus if they added some more things on top of the calculus. But these are the key rules for the operational semantics for effect handlers. So as long as you understand these rules, you understand basically what effect handlers are doing. Yes?
What's the meaning of the hash in operation?
Right, so this notation says that no handlers inside this capital E will handle this operation. So this rule only applies when this handler H is the innermost handler available for your operation, because you could have multiple handlers that handle the same operation in your context. So if you can only take one thing out from the whole lecture, then you should remember these two operational semantics rules that will help you a lot when you read papers on effect handlers and also understand what effect handlers are doing, and when you see an effect handler program, you can reason about how it runs and what result will it produce. So people use effect handlers for lots of advanced examples as well. So I have put one here just to demonstrate the expressiveness power of effect handlers. So you can use them to implement lightweight cooperative threads, basically a way to do concurrency. So on this slide, I'm using some syntactic sugars because I don't want to use explicit applications everywhere. So I'm using this left arrow just to mean that we will first evaluate this and then bind the result to this, and then continue with the computation. It's just a syntactic sugar for applications. So what is happening here? Like on this slide, we have lots of operations, and then we have lots of things going on in the handler as well. So basically, what we want is, well, because you have effect handlers, and because you have delimited continuations that capture the rest of the program, you can actually consider those continuations as first-class functions, right? You can store in a data structure, you can pass it around, you can do whatever you want with them. And in this case, what we want is, we will assume there is a data structure, which is a queue. And we can push things into the queue, and we can get things out from the queue. So I will just use in queue and d queue for that. And this handler, let's look at it line by line. So it's not that complicated, actually. It's just messing up with the continuations. So we have two effect signatures that says yield and then fork. And yield means I'm giving up the control of the program, and you can run whatever that is currently waiting to be run. And fork basically means you should run exactly the computation I tell you to run now, and you can put the rest of the continuation into the queue. So what's happening here is, if you call yield, right, you are basically saying, I want to give up the control of the program now. You run whatever you want to run now. Then this basically means we are going to put the current continuation into the queue. And then we are going to get the next computation from the queue, because maybe there are lots of computation waiting in the queue. And then we are going to run that computation instead. So you can see here, this continuation is actually used as a first-class function that you can actually pass around and store in data structures. Yes?
So what happens if something calls yield from within the next?
If something calls yield from the next, yes, you can do that.
Does this handler catch it?
Yes. It's exactly because we always, right, like all the things you get from the keyword data continuations, and all these continuations, they will really store the handler. So you can have as many operations you want in your program. They are always going to be captured by the same handler. And if you call fork, you are saying that, okay, you should run this computation G as an argument. So this computation G is a unit-to-unit computation, just for simplicity. Then it says, okay, I'm also going to not run the program that comes after me, but I'm going to call this function G, to run this computation G instead. And to run this computation G, and I wrap it again inside this scheduler, because this G might also call yield and fork. And this G is a random computation that you pass the A. It's not what you got from continuations. So it's possible they are no handlers, so you have to rewrite it again. Yes?
What kind of thing is scheduler here?
What kind of a thing is a scheduler?
It's like, I mean, is it like a function, or is it like?
Oh, yeah, it is a handler.
Okay.
Yeah, it is handler, but you are not giving the computation that is to be handled yet. It's just defining a handler by itself.
It's okay. I didn't realize that it's called scheduler and it calls itself. I was like, where did scheduler come from? Like,
Oh yeah, this is a whole function that takes an f and then handles this whole computation using this handler. And then if you return, if the computation finished, right? In this case, everything is a unit, so you don't care about the value, but you just get immediately the next computation to be run in the queue and then run it. So I'm assuming there's always something to be run in the queue, but of course there will be cases the queue is empty, then the whole program should finish. So this scheduler then takes a computation F that then actually calls this computation F and handle it using this handler. So as one example, right, you can pass this whole lambda as a computation to scheduler. And you can see there are lots of prints, so I assume there is some print effect that actually print things out. And there are lots of fork and yield. So my question is, what will be printed? Yes?
A, B, C, D, F, G, F, G, A, B, C, E, G, F, G?
A, B, C, E, D, F, G. Any other answers? Yes?
A, B, C, D, E, F, G.
A, B, C. The letters are there for a reason. So yes, A, B, C, D, E, F, G. So why? So we can look at this quickly to just to see what's happening. Well, of course, first A will be printed, right? And afterwards, you say, let's fork this computation. So this computation now will be run immediately, and this whole thing that comes after this fork is going to be put in the queue as a conjugation. And now you run this thing, and you print B. And now this thing yield. So this thing yield, you are going to put this print E into the queue, and you get this thing from the queue to run. And in this case, the thing in the queue is this thing. Then print C, and then you fork. And when you fork, you put this print F into this queue, and then you run this computation. And then you print D, and then you yield, so you get the next thing available in the queue, which is this print E that you put into the conjugation. And print E finished. Okay, when you yield, you will also put this print G into the queue. And now you run this print E, and it finished. You'll get the next thing to run, which is print F, and it finished, and then you run the thing in the queue, which is print G. Okay, so if you can actually understand this program, you have captured the essence, the exact essence of effect handlers. Because this is, I think, one of the very complicated but still small-scale example that you can write with effect handlers that demonstrate the power of capturing the conjugations and resuming and pass the conjugations around as first-class citizens. So I will give you so in the rest 10 minutes, I will give you a very quick overview of the other kinds of operational semantics that you might see from the literature. Because the thing that we have seen here, well, it is the standard semantics of effect handlers, and it is the original definition of effect handlers as well. But you will see different variants of effect handlers that appear in the literature, and because they are useful for certain cases, like it makes it easier to program certain examples. So this standard form of evaluation for effect handlers are sometimes called deep handlers because you reinstall the handler inside this continuation. So whenever you continue, the operation is going to be handled by the same handler. And there is also a version of the operational semantics that people call shallow handlers. And it is shallow because the continuation you capture, it still captures from where the operation is performed to where the handler is used to handle it, but it does not reinstall the handler. And it's sometimes convenient because you want to maybe switch to a different handler for the rest of the program, or maybe you don't want the rest of the program to be handled again, but there are some other things going on in the program. And there is a version of handlers that people use, and the semantics combine deep handlers and shallow handlers. For that kind of handlers, how would you name such kind of handlers that combines deep handlers and shallow handlers?
Medium.
Medium.
Hybrid.
Either.
Hybrid.
Hybrid. Mix.
Deep shallow.
It's a real terminology that you can find in papers. So what is this ship handler doing? So it's a bit like shallow handlers. So the original handler does not need to be reinstalled, but it's also like deep handlers. Some handler has to be reinstalled, but maybe it's not the original handler. So you can see the continuation that is captured here now takes the handler, H prime. So then it resumes the original computation under this H prime. So now you know how people are creative in naming things. And there is, sometimes you will also see parameterized handlers. So they are basically handlers that can carry a local state with them. Like in this case, you can see that now handler takes 3 things instead of 2 things, and the middle thing, this S, is the state associated with this handler. And every time, you can also pass the state to this function F. So the function F always have access to the current state, and also you get the chance to update this state when you resume. So it's just a very convenient way if you have, for example, stateful resources associated with your handler, and you do things differently depending on the state. I would just add that parameterized handlers, they also do not increase the expressiveness of the handler, because you can still encode the stateful handlers, like the state of the handler as a form of deep handlers. And also, deep handlers are as expressive as shallow handlers, that they can encode one from the other. And that's probably the case for ship handlers too, but I'm not sure, because it's a weird handler. Oh, and I will add, ship handlers are actually what get implemented in WebAssembly. So it's not that weird. You have to get used to the terminology. And I have one example to demonstrate why shallow handlers are useful. And that is taken from the original paper on shallow handlers. So what they want basically is to implement a classic demand-driven Unix pipeline operator. So basically you have a producer and you have a consumer. And the producer can produce things that will get consumed by the consumer. So in this case, we will call them type and co-pipe. And type is basically the consumer that waits things, and co-pipe is the producer that will produce things. And this P stands for the producer, and this C stands for the customer. So what happens is, if you want to run this customer program, then this customer could say, I want some resources now, so I'm going to call this await. And if you call it await, then the control is to be transferred to this producer, because until the producer produces something, you cannot continue your program. And then you will run this producer program, and this producer program can call operation yield. It's a different yield from the other yield, but it yields a resource that the customer wants. And it yields a resource X that the customer wants, and then you pass this resource X to the customer, and then you switch the control to PEP again. And now you are going to store the rest of the consumer as a continuation, and you will run this customer. So what's useful about shallow handlers in this case, as you can see, is you are switching back and forth between two handlers. You don't want the original handler to be restored. As long as the customer calls this await, you want to switch to the producer that there is only one handler that handles yield. And if the resource is yield, you switch back to the customer, then there is only one handler for await. And as an example, you can have a producer that keeps producing once. Okay, that's nothing. Just keeps yielding and provide the value 1. And then you can call the customer with the producer once, and this customer just says, I will await for a resource. And you can try to run this program according to these definitions. And in this case, when you await, you will just get back a 1. And then the whole program will just be a 1. But you can await multiple times because infinite number of 1 will be produced by the producer. Yes?
So why doesn't the await give you an infinite loop? Because I would have thought that the await part sends you into ones, which goes into ones forever. But is it?
Right, very good question. So when you await, you would call this callback. This callback will pass the current continuation, what is nothing, it's just end of program, and you pass in this once as P. And when you run this P, it will call this yield. And the rest of the ones would be the continuation K. And you will call PEP with the rest of the ones, but you will resume the customer function with one resource you produce. And the customer function in this case just says, I will just go to return the value. So you do still have the producer as a continuation here, this P. It's just in this case, the customer does not call yield to call await again, so that P is not used. And so far, we talked about the standard semantics of effect handlers. There are two more variants that I would like to mention quickly. So when we say that a handler handles an operation, right, as I emphasized a few times, it's always the innermost handler that will handle this operation. But what if I want my operation to be handled by the second innermost handler, or the third innermost handler, or the fourth? Then such a behavior is not supported in the original operational semantics. So you have to add more things to it. And sometimes people would use the word masking, or it's sometimes also called lifting, as a way to skip some of the handlers when you search for the handler to have your operation. So if you lift it once, then it's going to be the second innermost handler that will handle your operation. And if you lift it twice, it's going to be the third innermost handler that will handle your operation. And to do that, we just need to change the criterion under which we are searching for handlers. And now, in this case, you would say, I want this evaluation context E to be 0, free for all. And here are some definitions for this free notation. So an empty evaluation context is always 0, free. And if you have a lift, then you can say it's M plus 1 free if the evaluation context is M free. And if you have a handler, you can say it's M free if the evaluation context M is M plus 1 free. as an example, so what number should I put for this evaluation context? 0, right? Because I will say this is 0 free, and according to this definition, I want whatever is under the handler to be 1 free. And what I have under the handler is the lift, and the lift is 1 free if the innermost evaluation context is 0 free, and empty evaluation context is 0 free. And now, you would actually, when you try to handle an operation using some handler, this handler is actually going to be skipped, right? Because now this whole evaluation context becomes this capital E in that 0 free location. And programming with masking and lifting is a bit like deep red indices. Like you always have to manually specify which handler you want to handle this operation manually. And that's why my collaborators and I come up with a semantics for effect handlers that we call name handlers. That is, you can basically give names to your handlers. And when you handle operation, you can specify which handler you want to use to handle this operation. And here are the 2 key rules for such a semantics. Now I have 2 forms of handlers. So now I have a form of handler, and then I have a form of handle. And the handle is always indexed by a specific label. And this handler now handles this computation by taking a function, and this function, inside this function, this x, this variable x, will stand for the name of this handler. And in the operational semantics, you always generate fresh labels that you use to attach to those handlers. And now within this expression, you can use this x as the name of the handler. So whenever you get to the point that you actually want to perform an operation, you have to pass in explicitly that the name of the handler that you want to use to handle this operation. And now I will skip all those evaluation contexts that might have handlers for the same operation or not, but I will try to find the handler that is tagged with this specific label and then use that handler to handle this operation. And there are, of course, lots of subtleties in the operational semantics as well, because you have to make sure that the name of the handler does not escape. When you try to search for it, it should always be available in the evaluation context. And there are like higher ranked types, that basically rank 2 types that are involved in the semantics to make sure names do not escape. And just a very quick example. For example, now what you can do is you can have 2. Okay, here I have a reader handler that handles the operation read. And in this case, this read function takes this x, and then it makes the handler that whenever you call read, it will resume the